Hi, this is Jialian. Today I'm going to present our paper, What Every Scientific Programmer Should Know About Compiler Optimizations. This is a joint work between College of William Mary and Scalable Machine Research. Let's start our story from the view of compilers. As we all know, compilers are an important component in the modern software stack. A compiler is a tool to convert the text of source code into machine code, and the machine code can then be executed on the machine. In the meanwhile, compiler employs varieties of optimization techniques. Here we show a traditional 3-end modern compiler. The front end focuses on understanding the source code. The back end focuses on mapping programs to the target machine. And to improve the translation, a compiler often includes an optimizer that analyzes and rewrites intermediate form. The goal of compiler optimizer is to remove unnecessary computations and eliminate redundancy, and move code to places where they are less frequently executed and achieve less workloads for the CPU and memory. And they usually result in a faster execution time. Through compiler optimization, we can reduce the size of compiled code, improve the runtime speed, and use less register and memory, and have less energy consumption. Just because compiler can do so many things, as programmer, normally we treat compiler as a black box. We simply expect it to provide the high optimization level for performance. But the truth is, software from various domains have become more and more complex. They integrate multiple components to achieve the heavy functionality. They employ sophisticated control flow and component library hierarchy. The increasing complexity introduces inefficiencies with no doubt, which also creates huge challenges for compilers to optimize them. And we claim that the compiler-related inefficiencies do exist. Sometimes compiler optimization may cause more harm than good. There are two main categories of compiler-related inefficiency. First is the compiler-introduced inefficiency, which are not existing in the source code but appear in the compiler-optimized code. Another one is compiler-missed inefficiency, which indicates the optimization opportunity that compilers are supposed to do but fail to do. These inefficiencies are related with compilers' behaviors. They come up during the compilation process and expose the limitations in modern compilers. It's difficult to detect them because some of them do not show up in the source code. Therefore, to study the compiler-related inefficiency is very important, but in this research area, there's a lack of standard datasets for the experiment. So we want to introduce a benchmark suite that can reveal compiler-related inefficiencies. And our approach to detecting them is to identify runtime inefficiency. We mainly focus on the redundant computations. And not all inefficiencies that we have detected can be eliminated. They just give you an upper bound on how many inefficiencies exist for that input. To find suitable programs to form the benchmark, we first develop a tool, CIDetector. And CI is short for compiler inefficiency. And we use this tool to analyze the many software programs and pinpoint inefficiency to guide code optimization. Under the guidance of our tool, we are able to find suitable programs, and our metric is the speed on the generated optimized code. So CIBench is composed with 12 representative programs with compiler-related issues. We compile them with state-of-the-art compilers and observe their behavior. We aim to focus on the implications of compilers' evolution on inefficiency optimization. Not only the same compiler with different releases, but with different vendors of compilers. Our tool can catch some inefficiency pattern. First, it can detect dead stores. So dead store means to store values to the same memory location and no interwindow between them. So for example, a memory address is first assigned to 1 and then assigned to 2. Between these two operations, there is not a load, which makes the first store operation redundant. And then we have redundant stores, which means to store same values to a memory location. For example, first we store 20 to a memory address. Then the memory address is loaded, and another store operation writes 20 to this memory address again, which makes the second store redundant. And last inefficiency pattern we would like to catch is redundant load, which means to load same values from the same memory location. For example, first we load the value from BI, then the preceding load instruction loads the same value from BI, which makes the second load redundant. To detect the buffer inefficiency pattern, we need to monitor consecutive instructions that operate on the same memory address. And we also want our tool to be compiler independent, because we want to study a variety of modern compilers from different vendors, not only just focus on one compiler. So we choose Intel Pin tool, which is a dynamic binary instrumentation framework. We use it to instrument memory and register access, and to detect the inefficiency pattern we mentioned before. Here is an overview of CIDetector. There are 5 steps in CIDetector's workflow. They are initialization, instrumentation, analysis, storage, and output. The CIDetector can trace calling context for each dynamic instruction with moderate overhead in both runtime and space. And through the usage of our tool, we select some intuitive programs to form the benchmark suite. We can see that the CIBench covers 12 representative programs from different domains, like bioinformatics, image processing, system software, and we have detected all inefficiency patterns we mentioned before. And through further investigation, we categorize these inefficiencies into 7 representative types, and I will explain these types in the following slides. Our study studied the compiler behavior from both vertical and horizontal perspective. Vertically, we choose 3 versions of GCC to study the implication of GCC compiler evolution on inefficiency optimization. Horizontally, we analyzed the 3 latest releases of state-of-the-art compilers, GCC, ICC, and LLVM, and to study how they are going to handle cross-different compiler-related inefficiency. And we have enabled the highest optimization level for them all. Now let's start from the first inefficiency type, value hoisting. Here is a problematic code, and this code is holding in a 2-level nested loop. We can see that in the original code, the store to MCK in line 2 and line 3 didn't form a dead store because the MCK is used in line 2. But in the optimized code, we can see that after the first store, the value of MCK is hosting in the register EAX. When the conditional check executes, it compares the value from register directly. So the store in line 3 overrides the previous store in line 1. This is a value hoisting inefficiency, and this type of inefficiency is introduced by compilers. We optimize this code by using a local variable to record the value and write it after the conditional check. And this figure shows our experiment. You can see that the x-axis means different compilers, and the left y-axis means the speed up, and the right y-axis denotes the percentage reduction in dead store and total store. We can see from the picture that all GCC and LLVM compilers suffer this inefficiency, but not ICC. ICC does not yield any speed up, instead it shows a slowdown. The reason is because our optimization hurts its loop vectorization. So for ICC compiler, a better way is to use the keyword restrict, which will avoid producing dead store and generate a better vector code. The second type of inefficiency is instruction scheduling. And here we show the problematic code snippet. And this function has 12 successive conditions. Here we only list 3. And this condition checks the accesses of array block I1, block I2, all through block I1 plus 11 and block I2 plus 11. And this function returns when any check fails. We can see that the source code does not show up with any redundancy. But if we look into the compiler optimized code, we can see that the compiler aggregates address computation of array block before the first conditional check. However, there is not enough registers to store all the pre-computed address, so they are spilled to the memory. And because the function actually returned in the earlier part of check, which means that many of the computation are useless, and here comes the redundancy. And it is due to the compiler inappropriate instruction scheduling. To optimize this case, we use a switch statement before the conditional check. So through our experiment, we can see that only the GCC4 has suffered this inefficiency, and all other latest compilers do not aggressively schedule instruction, so they do not suffer from this inefficiency. And the third type is suboptimal scalar replacement. So we can see the code in line 8. The value of cache size is repeatedly loaded from memory because it is a global variable. The compiler assumes it can be modified at any time. So we optimize this case by assigning the cache size to a local variable so it can be held in the register. And through our experiment, we see that among all compilers, none of them eliminate this redundancy. The fourth case is identity computation. So we can see from the code that R2 is often assigned with the same value, and A2 is a loop invariant. As a result, the expensive exponential computation will produce the same values in the loop. For optimization, we manually insert a conditional check before line 4. So if the value of R2 keeps on change, then we will use the result of Vij from the previous iteration. And through our experiment, we found that all compilers do not eliminate identity computation. And the next type is function inline. So the problem in this case is that the function strength will keep popping the same value repeatedly from the same stack location to restore the register values. The compiler does not inline strength because the function's definition and invocation are from different libraries. And to optimize it, we manually inline strength to its call site. Through our experiment, we found that all GCC compilers do not inline the problematic function, and LLVM performs a different inline strategy, resulting in a different performance behavior. And the last type of inefficiency is limited inter-procedural analysis. And we can see that these two functions include code to check whether the TLab is equal to a null pointer, which makes the second check redundant. and the compiler does not perform the optimization due to the limited interprocedural analysis. So to remove the redundancy, we inline these two functions into their caller and remove the second redundant check. And through our investigation, we found that all compilers failed to eliminate the redundant check across the function call. According to these case studies, we have summarized a few observations. From scientific programmers' perspective, first we need to know that even modern compiler has been well designed, there are still lots of inefficiencies exist in fully optimized binary codes. And to accurately target the compiler's limitation, a standard benchmark suite is demanded. And furthermore, obtain a better understanding of compiler optimization is very important. It can help programmer to write efficient code. And from compiler writer's perspective, all compilers have some flaws in optimization techniques. The majority of inefficiency in CIBench cannot be eliminated by modern compilers, which reveals that there are still plenty problems in compiler optimization technique. And the compiler optimization technique is still a promising research topic that worth further exploring. And our study shows that different compilers behave differently in every category of inefficiencies. And we suggest compiler vendors should learn optimization technique from each other in the future releases. And also for a tool developer, we have two little suggestions. The first one is to evaluate the optimization trade-off between dead operations and redundant operation with other inefficiencies. And second, we suggest to a developer to develop some new metrics to quantify the speed up after compiler optimization. And to conclude, we perform systematic studies on compiler-related inefficiencies. And we provide valuable insight for HPC programmers and compiler writers. And we develop CIDetector, which is an inefficiency detection framework. And we also introduce CIBench, which is a suite of benchmarks. So CIDetector has been integrated into CCTLib, and we have open sourced them all. You can go check them from these links. We also study 5 state-of-the-art compilers and demonstrate their strengths and weaknesses. And finally, we encourage you to contribute more inefficiency detection tool and interesting benchmarks. And that's all. My presentation ends here. Thank you all for watching.